And then we come to the first order system. So we have first order system and we have second order system. For the first order system, let's say we have a system GS. Okay, we have A over S plus A. And if the input is a unit step where Rs equals to 1 over S, what we have here is we have the output CS equals to Rs multiplied by GS equals to A over S plus A. So I hope everyone can understand how we get this expression. Okay, and then when we put it into a time domain, we take the inverse Laplace of the expression CS. What we get is we get CS equals to CFT plus CNT, which equals to 1 minus exponential negative AT. So the order of a system is defined as being the highest power of derivative in differential equation, or being the highest power of S in the denominator of the transfer function. So what it is said is, remember the last time we have for the mechanical system, for example, if we have something like A over S square M plus S B plus C. Okay, so this system is actually second order system because the highest power of the S is 2. So this is second order system. In this case, we have GS. So the GS is A over S plus A. So the highest power of the transfer function GS here is 1. S power of 1. So we have the system is first order system. So a first order system only has S to the power of 1 in the denominator, while a second system has the highest power of S in the denominator of being 2. Okay, this is what I explained just now. When you see the response here, 1 minus exponential negative 80. So this is actually, we can classify them into, this is the forced response. This is the natural response. The forced response is due to the input being given to the system. And the natural response is actually the response of the system itself. A over S plus A. This is the response of the system itself. So you can see here, so this is the response characteristic that I have explained in the previous chapter, in the introduction chapter. This is the elevator response. We have the transient response and we have the steady state response. Okay, so as the time approaching infinity, you can calculate the steady state error. Steady state error. What does it mean by the steady state error? For example, in this case, we want to go to the 4th floor. So this is 4th floor. You press the button 4 on the elevator. So what you expect is that you go to the 4th floor exactly. So the level of the elevator is the same as the floor. When you walk out from the elevator, it shouldn't be any difference between the floor and the elevator. It should be stopped on same level. Okay, so this is the input that we have given to the elevator. So the elevator have a transfer function. Let's say we have G, and the G transfer function. So when we give, here is a step input 4, you can see the error by calculating where the elevator stopped at t approaching infinity. So if the elevator is in the same level to the floor, means that the steady state error equals to 0. There is no difference. But if, let's say, the elevator stops slightly below or slightly above the 4th floor, you will have some error. Okay, meaning that the given input minus the final output. That is the steady state error. So this is the given input. This is the final output of the system. So in the value here is actually the steady state error. Now, transient response specification for the first order system. We have a few time transient response specification that we can define from the first order system. So we have a time constant, we have rise time, and we have settling time. So what is time constant? Time constant is the time for the exponential negative AT to decay to 37% of its initial value. Or we can define it as the time it takes for the step response to rise 63% of its final value. Okay, let's say we have one minus exponential negative t, where t equals to 1, we have 0.63 to 1. So this is the time constant. For the rise time is the time for the waveform to go from 10% to 90% of its final value. And the settling time is the time for the response to reach and stays within 2% of its final value. Settling time also can usually by default is defined as 2%, but we can also define the settling time as 5%. So it depends on the questions. So whenever it's settling time, so by default it's 2%, unless stated settling time at 5%. Time constant is here. Okay, we have from 0 to reach 63% of final value. 63% of final value. Or in other words, it is the time taken to decrease to 37% of its initial value. So 37 plus 63 become 100. So it is two definitions with the same concept. 63% is not here. It's actually over here. Okay. All right. So this is 37% decays to its initial value, or 63% from the final value. So the rise time is the time taken to reach from 10% to 90%. To 90%. So the time taken here is actually the rise time. The settling time is the time taken for the system to stay within 2% of its final value. Because when reaching the steady state, maybe it takes time to become stable, something like this. So in between, maybe it has some oscillation over here. So it oscillates before it reach the stable value. It is actually between plus minus 2%. Whether it oscillates plus positive, plus 2%, or it oscillates downwards, negative 2%. So it oscillates. So the settling time is the time taken to reach where the systems stays within 2% of its final value. Okay, next slide. We have here the time constant tau is equals to 1 over A. Tau is equals to 1 over A. So when you see in the previous slide, we have, let's say we have the expression of output CT equals to 1 minus exponential negative AT. So the time constant is defined as the time taken for it to decrease to 30%, 37% of its initial value. So here is actually when we want to find it, we put it, for example, is let's say our T is 1 over A. So what we have is 1 minus exponential negative 1. So try to calculate using your calculator. What you get is 1 minus 0.632. So you will get about 0.37. The time constant is actually this expression here, 1 over a. Okay. So what we have is, for the time constant, is tau equals to 1 over a. Okay? Tau equals to 1 over a. For the rise time, so this is from the calculation given. We can use the rise time is actually 2.2 over a, and the settling time is equals to 4 over a. For the rise time and for the settling time is they found it by numerically plot against the plot of the response here. So they calculate using the computer, and then you will get this expression for TR and for TS. Okay, let's see some example here. So let's say we have our first order system here is GS equals to K over S plus A, where our step response is CS equals to K over S plus A. Okay, so S here comes from the input, 1 over S, step input. So when you find it, the partial fraction, what you get is you get K over A over S minus K over A over S plus A. And then you have been given this plot. You have been given this plot. So find the transfer function of this plot. Find the transfer function of this plot. Just given the plot here, the first order system plot, and then you need to find the transfer function. Okay, what we can do here is we can find the time constant over here. Okay, remember time constant tau equals to 1 over a. Tau equals to 1 over a. So from this expression, we can find, we know that the tau is actually the time taken to reach 63% of its final value. So this is the final value. Okay, final value. So we can, let's say the final value is 0.72. So we can find the final value multiplied by 0.63. What you get is you get 0.73 multiplied by 0.63. I think it's about 0.45. Let's say 0.45 over here. So from 0.5 you can extrapolate here, and then you can find the value of time. So here tau equals to 0.13 seconds. Okay, 0.13 seconds. And then how to find the value of A? To find the value of A, we know that K over A is the final value. K over A is the final value. A is actually, we can find the value of A using this expression. We know that 1 over A is actually equal to tau. So our tau is 0.13 equals to 1 over A. So we can find the value of A. We can find the value of A. And then we can find the value of K, where K over A equals to 0.72. So we can find the value multiplied by A. So what you get is you get the value of K equals to 5.54. You get the value of A 7.7. So basically, this plot is actually when you plot it on the MATLAB, it is plot by this expression 5 over S plus 7 is actually. So see the resemblance of this the actual plot to the calculated plot, calculated transfer function. So 5.54 over s plus 7.7 is plus minus the same. 0.63 is actually comes from here. Remember the definition, this one. 63% to its final value, or 0.63 multiplied by its final value. So this is the 0.63 is the time, is the number that you multiply by the final value to find the time constant. This is the code to plot for MATLAB. So I hope you already see these slides, and then you watch the video that I have posted in YouTube, so you can relate this code to the output for the system, first order system. Okay, so to recap, by now you should be able to define the poles and zeros of the transfer function given for the time response of a control system, and then you will be able to describe quantitatively the transient response of the first order system. So when we say about the transient response of the first order system, you must relate to the three characteristics, which is the first one is the time constant, and then the rise time as well as the settling time.